So, in this lecture, we will go into the heart of the problem, right? Which is catalyst design, electrocatalyst design. How would you design a new catalyst for a fuel cell? Okay, so so in some ways, what have we done? Okay, so we first talked about how to model the energetics. Okay, uh, in a particular surface, okay, particular electrocatalyst, platinum. Okay, so first we will try to understand what makes platinum the best electrocatalyst right now, okay, and contrast it with two other things which are not good electrocatalysts. It's, you might have guessed, okay, the way we are approaching the problem. It's very similar to the way we thought about heterogeneous catalysts, right? It's based on Sabatier principle. Okay, we'll talk about that. Again, there also we showed three systems and talked about why one of them was better. All right. So in the previous two lectures, we talked about how do you get the energetics on a particular system, platinum. Likewise, we use a same procedure to obtain the energetics on three different materials. Okay, so we will try to see. Okay, so we will see why platinum is the best amongst these three. Okay, so if I compute along, the energetics along the reaction coordinate, we already discussed platinum. Take nickel. Nickel seems to bind very well with oxygen. Okay, so the binding energy of oxygen to nickel surface is very high, as opposed to, in contrast to nickel, gold is an electrocatalyst which binds very weakly to oxygen. Okay, so here it binds a lot. Oxygen binds very weakly to oxygen. Gold binds very weakly to oxygen. Platinum is somewhere in between. Because nickel binds very well to oxygen, if you look at the activation barriers for the next two steps, okay, going from oxygen to hydroxyl, going from hydroxyl to water, both activation barriers are very high. Okay. However, for gold, this step will not even happen. Okay, the activation barrier is very high here, but these two steps have no or very less activation barrier. Okay, so here for nickel, the first step is very easy, but these two subsequent steps are very difficult. For gold, the first step is very hard, but these two are relatively easy. Why platinum is an ideal electrocatalyst is all these things are reasonably easy. Okay, so if I look at here, this is down the energy gradient. Okay, down the energy, so there won't be activation barrier here. So compared to nickel, this step is less facile. But platinum is, for platinum, this step is more facile to compare to gold. However, when you compare platinum to nickel, platinum does second and third step much more easily than nickel. Okay, gold might do better than platinum in these steps, but it won't be able to do this step at all. Okay, so platinum is the ideal catalyst, again because of reasons, the logic of Sabatier principle. Okay, because all the three steps should be reasonably well optimized for platinum to be a good catalyst. Okay, so that is the essence. Okay, so of the logic. Okay, so we have categorized the metal in three categories. One where the first step is most favorable, because of which the subsequent steps gets hurt. The other extreme is the first step is least favorable, because of which the subsequent might be better, but the first step never happens for you to get to these steps. So, but somewhere in between is platinum. So, how did we to find what is the next step? Okay, so first you ask the question, take all take the typical elements, okay, and compute all the reaction intermediates. We can also calculate the activation barrier. Okay, so you calculate that, and then for across many surfaces. Okay, so you get that, and then you try to do this kind of analysis. Okay, via this, and then you develop a map. Okay, so this map tells you what are we. This is very again. This comes back to how you thought about catalyst design in heterogeneous catalyst. Okay, this is again a Sabatier plot. So you, along the y-axis, you plot the activity, rate of the reaction, okay, the current that can be generated in a fuel cell, okay, or rate of heterogeneous catalyst. And then, if you look at, if you remember ammonia synthesis or methanation, we plotted the activity as along the x-axis, we plotted something of a reaction descriptor, okay, which is an important quantity which controls the activation barrier. Okay, for example, if I plot the binding energy of gold, I can tell which is some things will be a bad catalyst, these two are bad catalysts, and which will be a better catalyst. Okay, so this is a critical descriptor for the reaction. So as a function of the reaction descriptor, which is the binding energy of oxygen onto the surface, I can plot the activity. Okay, if the binding energy is very negative, that is, if it binds very well, as in the case of nickel, again the activity is not very high. Not high. Okay, it's not going to be very good. Okay, so these bind even more exothermically. The activity is even lesser. And the other leg of the volcano plot, this is the volcano plot. Okay, it looks like a volcano. It is two legs. The other leg is gold. Okay, so it binds to oxygen in an endothermic manner. Okay, the first step is going to be not at all feasible. Okay, so the ideal catalyst, okay, which is platinum, okay, is somewhere in between. Okay, so so this is called the volcano plot, and these are the two legs of the volcano. Okay, so as a function of this descriptor, the activity gets optimized. Okay, so what is the next step? How do we find a better catalyst? Okay, this is a catalysis. We have thought about discussed catalysis in terms of monatomic metals. Okay, I have not made a better system. So how did you think? Okay, so you typically, if I want to replace platinum, that is because of it being expensive, what would I have done? I would have tried to mix a metal from this leg of the volcano plot with this leg of the volcano plot and obtain an alloy, right? So, okay, even before going into that, I can, all this information is presented, okay, in a slightly different manner. Okay, so this is, I'm plotting the activities like a contour plot. Okay, so as a function of, actually the binding energy of this and this are sort of related. Okay, as a function of both these binding energies, I am plotting the contour plot. Okay, so this gives you very high activity to low activity. Okay, so these are the regions of high activity, and as I go away, okay, extremes, I have low activity. Okay, so the same information that is presented in a slightly different, more colorful manner. Okay, so let's understand. Okay, so Sabatier principle is very important for, and we have to rationalize volcano plot. Okay, so what is this Bronsted-Evans Polarity relationship? So that if I to get the E activation barrier, okay, so the how to think about the activation barrier in terms of energetics of certain steps. Okay, that's the Bronsted-Evans Polarity relationship. I've talked about it in the first few lectures itself. You go and refer to that. So these are the important principles for electrocatalyst design. Okay, Bronsted-Evans Polarity relationship, Sabatier principle, and volcano. Okay, in fact, this is the most important principle connected to Sabatier principle. So how do you design new catalysts? Okay, so this you must have an intuition by now. Okay, so you typically you want to know whether I can go to the peak of the volcano. Okay, this is going to the peak of the volcano. Can I have better cathode? Okay, that's the goal. So you design metallic alloys. Okay, you combine material from this and this, and try to see whether I can reach the volcano peak. Okay, so so there are lots of issues with catalyst design, right? So it's not that this is not like making sambar or rasam, right? So it's not that making some dish in the kitchen. I cannot just arbitrarily take something here and something here and mix together. First, the crystal structure of these two elements should be in a particular manner for them to mix together. Okay, the heat of mixing should be negative. Okay, first they should be able to form an alloy. That is a first constraint. And sometimes they may not form a bulk alloy. They may form only alloy at the surface. Okay, these are all issues of physical metallurgy. Okay, so these have to be considered. Okay, so whether sometimes you may be able to see the alloy might not be. You may think the alloy is not formed, but when you add in oxygen, the alloy might be facilitated due to adsorbance, okay, oxygen absorption on the surface, okay, and then sometimes this near surface alloy, okay, you may not form a bulk alloy, but near the surface you may form an alloy, okay. These have been very, very rich themes in literature, okay, research literature in the last 15 years or so, okay. There's been very, very active research, okay, because these are all very critical questions. Energy is one of the most important questions in modern engineering and applied sciences. So, and see, there are two things towards electrifying the society, right? Two approaches. One is battery, another is fuel cell, okay? Both might be coupled to solar cells, which we will try to see in the next lecture or so. Um, uh, we talked a little bit about battery design. Here we are talking about fuel cell design, right? And then you try to, I mean, you can form a bimetallic alloy, you can form a trimetallic alloy. The complexity increases, the composition, structural complexity increases, and especially you're going to succeed if you can form an alloy as good as platinum using non-noble metals, using inexpensive metals. If you can generate a catalyst as good as platinum, you have a winner there, all right? So this is a map which I want you to remember. Okay, so this I tell all my students. Okay, this and what is that we are plotting? On the y-axis we are plotting elemental abundance. Okay, on the x-axis atomic number. Okay, so if you want to make a large area device, okay, a solar cell is a large area device. Okay, a battery electrode is a large. We need lots and lots of thousands of square meters of electrodes. Okay, if you want to transition to a renewable energy based economy. Okay, so to facilitate large area electrodes, we want to be making these electrodes using inexpensive materials. Okay, I've emphasized this in the previous lectures. If you are going to make electrodes only of, let's say, iridium, platinum, gold, okay, these are all jewelry materials, okay, rare metals, okay, these are all not something where you want to make an industrial, large area industrial product, okay. So you want to be making alloys, you want to be designing functional materials typically from here. Thankfully, lithium-ion battery, lithium is somewhere here, right? So all the silicon solar cells, silicon is here, okay? So that still we can, the solar cells are possible, okay? But if silicon had been here, or lithium had been here, kaput, right? So there is no way of using solar cells based on silicon, okay? So typically the emphasis of research is, can you make functional materials, energy involved in energy conversion and storage using materials in this region? Okay, this is even acceptable. Okay, but this is going to be very, very expensive. Okay, so this is a slightly dated slide, but this is the kind of logic you want to be thinking about. Okay, so let me stop here.